right, I think we are ready to start. We'll be starting on time. So welcome everybody. I'll be giving a talk introducing you to the new geometry functionality of Mathematica 10. And first half, I'm going to try to give you the whole picture of how it all fits together, the flows and the workflows. And then the last half, we do some exploration where we use it a little bit more. And there are several more talks in this conference that covers various aspects of it. So the big picture of what's happening, the things that are in geometry is regions. So there are many ways to create regions. They can use numbers, parameters, formulas, even graphics and other things, or geometry defined in various file formats and so on to create regions. From regions, there are various things that we compute, properties, like area and volume and distances and stuff. And there's a whole slew of solvers. But to just keep this sort of simple picture in mind, and we'll get through this pretty easily. If we break it down a little bit more, we have four kinds of regions. We have basic regions or special regions. These are things like ball and disk and line and so on. We have something we call formula regions. These are things that are defined by formulas, like implicit conditions that set up a region, or parametric formulas that define a region. Then we have mesh-based regions, and there are two basic types. They're complete, sort of full, detailed mesh regions, and there's what's called boundary mesh representation, where you give like a polygon, where you give a boundary curve or a boundary surface. And then there's something else, which is called derived regions, which are built from other regions. So like a Boolean combination of things is an example of a derived region, of transforming a region, and there are lots of them. Different kinds, there are four kinds of properties. Dimension stuff is very important for determining many things with regions. Membership, moments. Moments is things like area and centroid, distances. And then there's 5 different kinds of solvers: visualization solvers, integration solvers, optimization solvers, equation solvers, and PDE solvers that operate on regions. Okay, so let's start the tour. So a region is simply a point set of Rn. So all of our regions are embedded in some space, Rn. And in Mathematica, concretely, anything that's region Q is a region. So basic regions, they're simple and common, specified with a few parameters like ball. Formula regions, formulas. Here's a simple example. They're really flexible, but they get kind of complicated too. But they're exact, and you can get exact results. Mesh-based regions are very flexible, particularly sort of as a ways of approximating regions. They're specified with points and cells. Here's a typical region. Here's a volume region where you have a collection of volume cells, in this case tetrahedra. These can be in any dimension. They can be line curves in 3D and so on. They don't have to be full dimensional. Derived regions, they're very flexible and allows you to sort of derive new ones from old, so like a union. Okay, so let's look at some examples. So here are some basic regions or special regions. So geometry works perfectly well in 1D, in which case we have point, line, and interval. 2D, we've effectively doubled, so almost all the things that are graphics primitives before are now also geometry, special or basic geometric regions. But beyond that, we've doubled the number of such primitives in 2D and 3D. And so there are now unbounded regions, like a half line or an infinite line. There are other things that are more sort of high schoolish, which is side, side, side triangle, those kinds of things, and so on. Likewise, in 3D, you have some of the same things, but you have half plane, infinite plane. There are new unbounded ones, and you have various cells like parallelepiped and hexahedra, prisms, and so on, and very general things like conic holes. And a lot of these special regions work perfectly well in any dimension, in n-dimensional space. It's kind of silly to restrict yourself to 3D in Mathematica. Or just full dimensional 3D. It just looks arbitrary and silly, you know. Although it's very, very important case, so don't get me wrong, you know. But it's just okay. So let's run through some. I forgot to delete the outputs here, so you're going to see it. You know, here's an implicit region, and you see that there are two types. One is that we give a condition. You guys that have been using Mathematica and using region plot and other things have gotten used to this. And if you integrate using bool with conditions, you've gotten used to this, and you've probably already well warmed up. This is a way to represent it as a region and to be able to compute with it as a geometric object very cleanly and combine with everything else. Parametric region, it's just what you think. It's kind of like parametric plot. It has one more case, you know, which you can give a condition here, like a P condition for your parameter space. For those folks who come from the CAD industry, these would be called trimmed regions, where you give conditions on the parameter space. And here is kind of like a hello world case, like can you integrate over it? And so just doing that to show it's a real region. So this also indicates another thing, that if I want to integrate over a region, this is a 2D region, this is a symbolic vector variable, and says, like, you know, X is in that region, and just integrate over it. 3D one, hello world case again. And so that is implicit or formula-based regions. Now, mesh-based regions, they are, I'm going to sort of show two things here. One is that the mesh-based region, it's basically a disjoint union of cells. And so the case that you probably all intuitively have in mind is like a triangulated surface. That's a really good case. So that's a disjoint union of triangles. But they can be any kind of piecewise linear cells. And they can be in any dimension. So a curve with line segments in 3D is a perfectly good mesh region. So the other one, which is boundary mesh region, they're a little bit more compact. They're like polygon. You only represent the boundary mesh for it. So in 1D, it's 2 points. In 2D, it's a curve. And in 3D, it's a closed and oriented surface that you have to specify to give those. And works perfectly well in ND2. Not for us right now, but the theory it will generalize. Okay, so here's an example. For those of you who have used graphics complex, you can see this is the same idea, that the coordinates, the geometric embedding is separated. So these are the points, and these are indexes into the points. So the first triangle here includes points 1, 2, and 3, index 1, 2, 3, and the next one, 3, 2, 1. And this is, you know, for those of you who are used to graph, we can put properties on the individual cells that make up one of these regions. And so I can also use them as labels in here. So here is a collection of 2 triangles, the hello world test. Here's a collection of 2 tetrahedra. So here's the points. And down here is the multi-tetrahedron. Tetrahedron 1 is point 1, 2, 3, 5, and so on. Here's well, apart from the hello world test, the boundary mesh region. So I have a bunch of points. Then I can specify one boundary and another boundary. I can specify arbitrarily many boundaries. So these guys can have holes. The way how it's determined what's inside of a region is called the ray test. So if you put yourself at a point, you draw a ray out to infinity, any direction you want. If the number of times you cross one of these boundary surfaces is odd, the point is a member of the set. If it's even, it's not. So if I put myself in here and I put a ray to infinity, I cross 2 boundaries. It's an even number, so I'm not in. That very same idea works in any dimension. So here's a case of 3D where we have a hole inside. So there are 2 surfaces. There's an outer surface and an inner surface. And the test for membership is exactly the same ray test. You draw a ray to infinity, and you count the number of times you cross the surface. So if I put myself in the middle here, and I draw a ray to infinity, I cross 2 surfaces, an even number, so I'm not in. Hence, it's a hole, a void. Okay? There are other kinds of holes that naturally come up. They're usually called tunnels, just because there's this distinction, right? You have tunnels and voids in 3D. And, you know, what do you mean by hole? Do you mean a tunnel? Does a donut have a hole in it, or a tunnel, or a void, or anyways? This is a pretty complicated way to build them, but it's still very powerful to be able to do that. So most of the time, you're going to use other kinds of constructors to build these mesh regions. You can build a Delaunay triangulation. It's called Delaunay mesh, so it uses it builds up this collection of simplexes. So simplex is the generalization of triangle or interval to any dimension, and this one builds up a collection of those. Voronoi, which we will see a little bit later, builds a, for each point that you give here, it will give you the cell that is of set of points that are closer to that point than to any other point in the set. Okay, it's really an infinite region. So there's another argument that you can say which region you want to look at it, and mesh regions can only represent bounded regions. Convex hull mesh is effectively the outer surface of that Delaunay triangulation, and it is a convex set. So surprisingly, guys. Now another thing is that one way that we can build up mesh region is to discretize graphics. So graphics contain both piecewise linear primitives that can be represented exactly, and nonlinear primitives like disk and ball and cone and so on. And these guys need to be discretized to a certain resolution. There's also many other useful utilities in these guys that allow you to filter out, say, how finely you want to discretize. Now, so I told this guy to build a boundary mesh region. And so that will, if I have a big graphic scene with lots of things, with lines, and sometimes things are diagrammatic, you don't really want that to be geometry because it was just like an arrow to illustrate something. I mean, we can integrate over that arrow too, but it's just, often you don't want to. It was just an illustration. So that one would fish out all the full dimensional things because it's the only thing that can be represented with B-reps or boundary representations. Now, if we triangulate, we can fill out the interior by triangulating it. And this is making use of what's called a constrained Delaunay triangulation. We can get, there's a lot of functions that I won't show about ability to drill down into meshes, but we have other talks later in this conference that will go into those much more. And this gives you the number of points, lines, and triangles. So the number of cells of different dimensions, 0, 1, 2. If I have a disk, here's a more complicated implicit region. If I run that, we can see how that comes out. And so these implicit regions can be quite complicated. They have ability to describe fairly complicated sets. You can, just this highlight graph and other kinds of functions, we have a highlight mesh that allows you to style and illustrate and so on. In this case, I tell it to style all the one-dimensional cells that are in there, and I want them to be red. So that means all the line boundaries. Final type of region is a derived region, and this is one thing that you will see grow a lot over the coming releases in Mathematica and Wolfram language. So there's Boolean operations, union, intersection, difference, symmetric difference. Symmetric difference is basically like an XOR of regions, the things that are in one or the other, but not both. Or a general Boolean function. You can see that all of these Boolean operations are effectively defined by Boolean conditions. Well, you can do it for any Boolean function, and we have a lot of them in Mathematica. Product is Cartesian product. Transformations by a mapping, or the inverse of that, the inverse image, or the boundary of a region. Okay, so let's do some simple examples here. There's a bunch of disks, and so here are the 4 most common Boolean operations: union, intersection, difference, symmetric difference. Let's look at some transformations. So here's a variety of affine transformations. And there's a huge library of affine and linear fractional transformations that you can do in Mathematica. It's a pretty rich set, and we'll be enriching that too. This is what that one does. So right now, it's sort of restricted to affine transformations for these mesh regions. That will be relaxed as we go forward. For the other kinds of regions, you can do any kind of transformation you want. Okay, so properties. Now, So a property is something that computes. It's like a statistic, if you like. If you think of probability and statistics, what's the mean? What's the variance? What's, some kind of property? So every one of our regions, they live in some space. And you've seen me showing mostly 2D and 3D. And so they live in 2D or 3D, but they can live in any D. The region itself has a dimension. And the dimension is determined by sort of the largest dimension a ball that you can put inside of it. So a curve, you can basically put a little interval ball, if you like, on it. So that's a 1D thing, and so on. That has some implications for instance, how we integrate. So if you tell in 2D to integrate over a curve, it will use a curve integral. It uses that dimension information to determine what to do. So we have membership properties. This asserts membership, and this tests membership and give conditions for membership. We have a lot of things. There are special names for 1D, 2D, 3D. But generally speaking, we can be any D, including 0D. Centroid gives a measure of what a center is of a region. It's one of many possible centers. Nearest, distance, and signed distance. The nearest point from a point to a region and what that distance is. So let's look at some examples. Okay, so here are some low-dimensional examples. So here is along the x-axis here, this is the dimension. Along the y-axis is the embedding dimension. So here's a point in 2D. Here's a point in 3D. It's still a zero-dimensional object. Here's a curve in 2D and one in 3D. It's still a one-dimensional object. Here's a surface in 2D and 3D. It's a two-dimensional object. And here's a volume in 3D. It's a three-dimensional object. And I could have extended it because we do support 1D embeddings too. 1D regions are perfectly good. 1D embedded regions. Okay, so here are some concrete examples. A disk, as we know, is a 2D thing. A circle, which is the boundary of that disk, is, they're all embedded in 2D. The circle lives specifically in 2D. Our circle does. And the point, this one that has four-dimensional sort of coordinates, it lives in 4D. Okay, but the actual dimensions are, the disk is 2D, the circle, which is the boundary of that disk, is a curve, so it's 1D, and the point, of course, is a 0D object. Now, we use element, or we typically use the typesetting notation element of, to assert that a point is in a region, like so. Now I can use that, and we'll see that shortly, as a way to specify that I want to integrate over that region. And this one had some parameters in it, so the result has some parameters in it. If I want to test for membership, or I get conditions for membership, I can use that, any of the regions that we've seen, 4 types, and I give symbolic parameters here, I can get the actual condition. And you can see that in this case, we also get, in fact, the condition on the parameter coming out. That's an assumption. The disk assumes that we have positive radii disks. Okay. Now, if I do the same region member without a second argument, then I will get a region member function that can then be applied to points, and that's very useful when you want to test membership many, many times. So it gives the same result as if I had given the point in that original function, but it provides this more efficient way, this more efficient representation that can be used. So here's an example where I generate a region, which is a convex hull, and I generate 100,000 points. And also, just instead of generating that region member function, if I give a long list, it will first build that function, that region member function, then apply it in parallel in a listable way to all of these. This last extension comes with 10.02. In 10.0.0, it's sort of a two-step process. And then I can visualize these 100,000 points, green for the ones that are in the region, and red for the ones that are outside of the region. Okay, so what about moment properties or integration-oriented properties? So we have special names that we all grew up with, like length, area, volume. But more generally, we have a measure function. And so the measure function will compute the generalization of volume to, first of all, points. And what the generalization there means, counts. That's the appropriate measure for 0D objects. And the generalization for volume for 4D, 5D, and so on. So it will look at your region and says, what's the maximal dimension? That is the dimension of your region. And then it will use the corresponding definition. Centroid integrates sort of the moment and divides by the measure. Okay, so here are some examples. If you the area of a circle is 2 pi, the arc length of some implicit thing, and here we can see it's an ellipse. It computes, if you give exact input, it tries to give exact outputs. If I had approximation on the inside, it will use approximate methods. But if I use exact input, you get the real true thing. This is a perfectly good curve for us. It's very much not manifold for those who cares about that. I found that most things in the world are not manifold. So the area of a disk, these are things that we all know, are that's a boundary mesh region. The volume of a ball, we know. Volume of some mesh region. But here's an example of a sort of a convenience. The n, if I give an integer argument to sphere, it will give me the n-dimensional unit sphere. So these are the volumes, the measure, which is the areas of the n-dimensional spheres up to dimension 10. I can use some other functions in Mathematica that we had for a while that looks like a sequence. So maybe I can identify what the general formula is from that. And in this case, find sequence functions is able to find it. But this was simple, and we know that, and you can look that up. But you can use that for many more general things, and it actually works surprisingly well. Okay, so the centroid thing gives you a sense of where the center is of a region. So as we know, the center of a disk is just the middle point that we use to specify it in Mathematica. We can do centroids for anything. Now in this case, I give the polygon that I gave here is not convex. And one thing that can happen that you should be aware of is that centroid doesn't necessarily lie in the region unless it's convex. But again, these mesh regions, they display themselves, but they're still regions. And so I can just use that as an argument into any function that works with geometry. And this is the center bunny. Okay, it's just more fun with cows and bunnies than disks, and we can sort of leave spherical cows. Okay, region nearest. So if I have a point and a region, what's the nearest point in the region to that point? And what's the distance to that nearest point? And then something that's slightly more subtle, which is the sign distance. And if that's a point outside of the region, then it's the same as distance. If it's a full-dimensional region, let's say a disk, then that's the distance to the complement to that disk. So it's the distance to the boundary. And it's negative when it's inside. And so it gives you a different name. Different domains have different names for these things. Sometimes it's called the depth of a point, that negative. Okay, so again, if you give these symbolic arguments to it, like we saw for member, we'll give you actually a closed form for it. Now these can be pretty complicated, except for a disk and ball and so on. Here's, for instance, for a triangle, and even that got sort of surprisingly complicated, but they're very fast, as you'll know. We spent a lot of time deriving these. Again, if I don't give a second argument, it will give you a nearest function, something that you can compute. If you want to do this a lot, will provide an optimized form. And the ones that you can see what that optimized form would be when we have formulas, but for mesh region, it's not formula, it's a procedure. So if I apply that to a bunch of them, it will give me the nearest point for each and every one. Okay, so distance, as we said, is the distance to that nearest point. And it works pretty much the same way. If I don't give a second argument, it will give me a distance function. Apply that in this case, and I can plot these iso-distance curves from the triangle. So the triangle sits here in the middle somewhere, and I'm at distance 0.25, 0.51. Or I can do the same in 3D. Should be pretty fast. And the style sheet has some weirdness. And so now we come to, so that's properties. There's a few more, but those are the most important ones. Now, solvers is one thing that makes it a lot of richness to use geometry, and it gives a lot of enhancements and enrichments to the solvers themselves. The one important thing that we finished, but we didn't document for 10.0.0, but it will be part of 10.0.2 that we're about to drop, is to be able to plot over regions. You still saw examples of us doing it in the literature, but it was sort of more select examples. And for 10.0.2, it will work really well. So I kind of have stylized versions here. So you can plot a function, and you just indicate where you want that variable to lie, what region. Same idea works for integration, symbolic and numeric integration over region. Same idea. We can solve PDEs, and there was a great talk yesterday, and there will be a workshop on it this afternoon, and so on. We can solve PDEs over regions, and we can even solve with maintaining parameters in that PDE and do sensitivity and other things. We can optimize over region. This is a little bit more general than it seems here, because I can have any number of extra region constraints like this in my constraint list, but I wanted it to look similar, so this is the way it looks. So I can optimize over a region, and I can solve equations and inequalities over regions. So that alone, so here's about 30 different solvers that now today work on regions. Okay, so here are some examples of plotting. So I give a bunch of intervals here. That's what it comes out to. And who said that the sine function wasn't monotone? I mean, it's depending on what domain of definition you use, right? So, or I plot sort of a function over a disk, or I can do these vector plots, like stream plot over a disk and so on. It works with any region, any of the things that you've seen me show, okay? Likewise, we already seen a lot of examples of integrate because I've been using it sort of as a hello world thing. One thing to remember though is this, what I said, like in the case here, where I give it, this circle lives in 2D, but it's a curve. And what integrate will do, it will do a curve integral in this case. So if I integrate 1 over a curve, it will give me the measure of it, in this case, the length. If I integrate over a disk, it will do a 2D integral. If I integrate over a ball, a 3D integral, and so on. This is, again, a perfectly good curve to us. Very much not manifold. And this is the length of it. This is actually, it looks like a volume. You can't tell the difference between surfaces and volumes. This one is a surface. So this is the surface area of that cow. This is a volume. And we'll see more of this guy a little bit later. It has tunnels going in every direction. So that is integration. PDEs, I'm not doing it justice here at all, but we had a talk yesterday. We'll have a workshop this afternoon. And I know you guys are really interested in it. And so if I solve, this is a Poisson equation. I give some very kind of basic Dirichlet conditions. I want it to be 0 at the boundary. You can see that here in the plot. And then I just solve it over a disk. So I can now plot it over a disk, which we just learned. I do, the previous talk, John talked about PDF import. Well, we can import the outlines of fonts. And that's a perfectly good mesh region, or boundary mesh region. So I did that, and there it is. And now I can solve the same equation, effectively, over Wolfram. And so here's the Poisson equation solved over Wolfram. I tweaked the right-hand side to get them to droop the right amount. Okay. We can optimize over regions or with region constraints. So here's one of these 18 optimization functions. I want to just I want to find a minimizing point for that over a disk. And there it is. I can find a maximizing point. And if we show that, I think that this is useful first time you start with teaching optimization to show the level curves, and this is the minimum and as the maximum attained at the boundary. These things get very easy to explain now, whether it's just class or just a report or something. Let's take two other regions, and I want to find the minimum distance between these two regions. So I have one point being in region 1, the other one in region 2. What is the minimum distance? And one thing that you see me use here is these symbolic vector variables. So notice I didn't do all the components here. These are 2D regions. And what I get out is the results, the 2 points, or I can find the maximum distance. And here is a visualization of that. So that's the minimum distance points and the maximum distance points. Last group of solvers are equation and inequality solvers. So let's say that I want to find the intersection between two lines. So here is line 1, line 2, and just find me the x's and y's that cross it. And here's a visualization of that. Or a line and a circle. In this case, I switch over to use these symbolic vector variables. And there are those, and that's an illustration of that. Or I want to find the intersection of 3 spheres. So I do use my 3 spheres, and I want to find a point that's in all of them. That turns out to be 2 of them, the way I place the spheres, like so. Okay, so here's what we've done. You now know everything, okay? This is the whole thing. This is the story. This is it, okay? So just to recap where we were at, there are regions, and we saw there are 4 kinds of regions, 4 kinds of properties, although there are many more actual concrete properties, and 5 kinds of solvers. And there are many concrete solvers, like 30 of them.